Okay, this is the lecture video for MAC1114 Trigonometry. We're in section 9.4 where we're going to take a look at the properties of vectors. As we begin this section, I'd like to establish the difference between a scalar quantity and a vector quantity. A scalar quantity describes the magnitude of the object, and magnitude is just essentially the size of the object, whereas a vector quantity signifies magnitude as well as direction. And you can see a picture of a vector here. Here is the vector. The magnitude is 10 and the direction angle is 30 degrees. So this vector, you can tell that it has rotated a positive 30-degree rotation off the horizontal. Vectors are represented using different notations. You can have two capital letters with no arrow on top, or you might have two capital letters with an arrow on top. They are often bold-faced, the capital letters, but sometimes not. You can also use lowercase letters. A single lowercase letter, typically bold-faced, and it might have the arrow, it may not have the arrow. So just different ways of signifying a vector. Okay, here what you see in this picture are two vectors that go by different names, and that's because we have a convention or an agreed upon way for naming vectors, always starting with the initial point and then describing what the terminal point is as the second point. So this vector, being that you have the blunt point here and then the arrow here, the blunt point is the initial point, and this is the terminal point, which you can tell because it's the arrow. The arrow is right there. So this vector, since we're always supposed to name the initial point first, goes by the name OP, capitalizing each one. Whereas this vector is called PO because this is the initial point, and this would be the terminal point. And since we need to name it from the initial point first, we would have to call this PO. So two different names, and you can see they go in different directions. Okay, in this particular picture, what we're trying to show here are two vectors that have the same size, but simply, as I stated before, they move in opposite directions. All right, then are some properties. There's some properties that we're going to share before we begin doing any kind of algebra with the vectors. One of the properties that we use is one that you've seen in algebra a lot, and it's called the commutative property. So for vectors, when you're adding two vectors, it doesn't matter whether you add, it doesn't matter the order that you use when you add the vectors, and that's referred to as the commutative property. You're going to get the same answer either way. The sum of two vectors is referred to as the resultant. So when you see that in the directions, let's try to get, familiar with that word so that we understand when you are asked to find the resultant vector, that means you're being asked to find the sum of two vectors. So just a little terminology for you. Another property that we often see in algebra, like we may see it as 2 plus negative 2 is 0. Well, here we call it the vector and its opposite vector. When you take a vector and its opposite vector and find the resultant or the sum of those two vectors, you get what's called the zero vector, a vector that has both components being 0. And we'll talk more about components as we go further into the section. Scalar product. As long as you are multiplying a vector, that this would be the vector u, here you can tell because it's darkened in and because they've already mentioned it in words here. If what you're multiplying it by is a positive value, then all that positive value does is change the size, or in other words, the magnitude. It changes its magnitude or size. But if you change the sign, let's say that multiplier all of a sudden is negative, which is what it means to be less than 0. If that multiplier is negative, then we change it with regard to direction. Okay, so here you see vector u. If you multiply it by positive 2, it's twice as big, but it still moves in the same direction. If we multiply it by 1.5, then it's 1.5 times as big as the original u, but still, again, in the same direction. If we multiply vector u by 1/2, then it's half as big as the original, but again, moving in the same direction. Then if we multiply that vector u that we started with by -2, then the direction changes. And that's what all of this is about. Depending on the multiplier that you use, you can either keep it going in the same direction but change how the size of the vector, or you can make it go completely in the opposite direction. Notice that all these vectors go up. This one comes down because it has a negative coefficient or a negative scalar as a multiplier. And moving to example 1, where we're going to start looking at vectors and learning how to draw them, learning how to do various algebra operations, and then learning formulas where we apply a combination of those things. Okay, so in this first picture, we have a specific vector, and just so you can, take a look at how to name a vector, and it makes it easy to pick what's the opposite of this vector. Well, for one thing, when two rays or two vectors are opposite to each other, they just move in opposite directions. One is just an extension of the other, but they move in opposite directions. If you want to go algebraic on this problem, then you can see here that the end of this vector, and this is actually how you name a vector, this is called vector B, and the specific components that name this vector it's just a point that you would plot at the end of this arrow right here. So this is 1, 2, 3, 4 units over, 2 units up in the air. You can always enlarge that on your screen if you have a digital copy, which you do, because this copy of this outline is attached to your Blackboard shell. But anyway, this is 4 over, so that would be your horizontal component, and it's 2 units up in the air. That would be your vertical component. So it's just like listing the coordinates of a point. We have different symbols for a vector than we do for a point. For a point, it's parentheses. So if somebody said, what is the opposite of this vector, which is what the question is, just take the vector, multiply by a scalar that is -1. Opposite of a vector just means that you are multiplying everything in the vector by -1 if you want to go algebraic on this problem and know exactly what you're looking for. It would just be -1 times this, -1 times this. So you know what the impact of multiplying by -1 is. It just changes the signs on everything. So if you're looking for a vector that represents the opposite of B, you're looking for -4, -2. And that would be this problem right here, or this picture. 1, 2, 3, 4, down 2. -4, -2. And you can see that this goes in the opposite direction as the original. Okay, moving to the next page, where we begin to look at how to create the sum of two vectors, again, also known as the resultant vector. There are 2 different procedures for showing it geometrically. We're also going to be doing it algebraically, but in this problem, we're doing it geometrically. And you can either use this method. There's 2 methods here. We're going to be using the parallelogram method. That is the one most commonly used in your mathematics classes, physics classes, all of that. But this is another way to do it. You can place the initial point. This is the initial point of one vector, and they're calling that vector B, right at the terminal point of vector A. So this is the initial point of vector B, and we're placing it right at the terminal point, which is where this arrow is, of vector A. And then you connect it with a diagonal, connect these 2 ends with a diagonal to form a triangle. That's one way to draw the sum of 2 vectors. In other words, represent it geometrically. But you can also use the parallelogram method. The parallelogram method is where you paste the initial point of both vectors, you superimpose them at the origin of an xy axis, and then you draw, after you have superimposed your two vectors, their initial points, you draw a line that is parallel to one of the vectors. It'll be opposite to that vector, same size, same slant. In other words, same slope. And then you take the other vector and do the same thing. Draw a side that is opposite to us with approximately the same length and same slant, thus forming a parallelogram. If you remember from your geometry classes and also in the algebra classes, they'll also talk about this. A parallelogram is a four-sided figure. Opposite sides are equal in length and also parallel. In other words, they have the same slope, same slant. So this pair of sides as well as this pair of sides has that going for it. And then from the point where the two vectors intersected, you draw a diagonal to the opposite vertex of your parallelogram, and that represents the sum. So here, this is the resultant. You need to get familiar with that word. It means you're finding the sum of two vectors. Here, the diagonal represents the resultant. Okay, so now we're going to look at example 2, and we're going to try and find the sum of these two vectors, A and B. So when you try and use, and all the choices are parallelograms, so we're going to be using the parallelogram method here. Okay, so if you're trying to draw your own, you can start off with a y and an x-axis. Draw one vector with its initial point right here at the origin with this approximate slope. Because, you know, the best you can do is approximate. You're not going to get it exact unless you start getting out, you know, other tools to get that done. So this is almost straight up, has just a very slight slant. That's going to represent A. Okay, then we're going to take and we're going to draw vector B. And vector B will take its initial point and also put it at the origin and give it approximately the same slant. I mean, from the horizontal, this is about 15 degrees up in the air. Not very high off the horizontal, so, and it's a little bit shorter than A. So maybe like that. That'll represent B. Again, you're just approximating these. And then you're going to form a parallelogram. So, opposite to vector A, we'll make this the side opposite to vector A. Making it have the same slant as this, and this will be the side opposite to vector B. Closing off my parallelogram. And then as you go from the point where both of these vectors have their endpoint superimposed over to the opposite vertex, and that represents A plus B, the resultant. Okay, so you want to find the picture whose resultant goes in that same direction. Okay, and you can imagine superimposing an XY axis to any of these, where this point right here was at the origin. See, this looks just like the graph that we just drew. This would be the y-axis. This would be the x-axis. This is the picture that represents what we just drew freehand. And you can see that the vector goes up. That's supposed to be the arrow. I'll darken in anything that you can't see. Here, this is the resultant. Here's the little arrowhead right here. Not too easy to see. And they're putting the A plus B right there, going in the wrong direction. Here, let's see, we have A and B. Looks like the arrow's going that way, wrong direction. And so, you know, you rule out each one of these based on those sort of things that's going on here. This is the resultant. They're trying to label this A plus B. That didn't come out too big, but that's going in the wrong direction. So this is the one that most closely resembles what we just drew. Let's see. And again, you'll be able to see these pictures a little bit more clearly when you're looking at the digital copies, and you can enlarge them for certain things that you can't see. I already enlarged these pretty well, but you know they don't take well to print. Okay, here again we're given vectors A and B, and you're going to try and sketch a graph that represents A minus B. So you're going to draw A as is, but you're going to draw B in the opposite direction. Okay, so here's, this will represent our y-axis, this will represent our x-axis. Okay, this will approximately be A. And then I'm going to do B. First I'll do just a light sketch of B, but then I'm going to go in the opposite direction. So taking that and just coming in the opposite direction, that will represent B. Okay, and then out of these two vectors, I'm going to construct a parallelogram. Okay, I'm going to try and make a side as long as A and approximately the same slant. Okay, that'll represent the side opposite to vector A, approximately same slope. Likewise for vector B, that'll represent the side opposite to B. And then go to the opposite vertex, and that represents A plus or A minus B. I don't know if I can fit that in there. And that's the same thing as A plus negative B. So that's your resultant, A minus B. And so the picture that looks most like that one would be going in this same direction as the resultant we created freehand would be choice D. Okay, then at the bottom of this page we have vector operations. And for these vector operations, we're talking about multiplying, adding vectors. So the first thing that we look at is when we add two vectors. Again, these are the symbols that we're going to use. This is called the horizontal component, just like the x-coordinate is the horizontal coordinate. This is the horizontal component. This is the vertical component. So if you have two different vectors, the horizontal component A and B, here the horizontal and vertical components are C and D. And if you're going to add them, all you do is add horizontal to horizontal, vertical component to vertical component. So front plus front, back plus back. And you get your new vector. This is how you find the sum of two vectors, but rather than geometrically, where we use this parallelogram method, we are finding it algebraically. If you are taking a vector with two components, again, these vectors have two components separated by a comma, and multiplying it by a scalar, you'll just distribute that scalar as you multiply to by both components. So k times A, k times B, that will represent your new vector. Okay, then this is what I've already said verbally. If you have a vector A that has a front component and a back component, well then the opposite of that vector is just those two components multiplied by a negative with their signs switched. Okay, if you subtract two vectors, okay, well it's up to you. You can multiply each of these by a negative and then add them together, or you can just go A minus C like that. B minus D. And this will be your final answer. We're going to carry all that out in the next couple of examples. Okay, so in example 4, they would like us to take vectors A and B and add them, subtract them, and also to just take vector A and form its opposite. So the first thing you're going to do is go grab the numbers off of the diagram. Okay, so we have vector B. This is vector B right here. And if you look closely at this, vector B, in other words, the end point here, the terminal point, which is where we grab the numbers from, is at 1, 1, 2, 3, 4. 1, 4. Okay, let's list that here. Vector B is 1, 4. Vector A, on the other hand, and we'll list the components of vector A as well, is at -1, -2, -3, and 1 up in the air. -3 for the horizontal component, +1 for the vertical component. Okay, so now we can go ahead and do A plus B, A minus B, and then the opposite of A. Okay, so here's A, -3, 1, and we're adding that to vector B, which is 1, 4. And then using the properties from the previous page, we're going to add horizontal to horizontal. And then we're going to add vertical component to vertical component. Coming up with a final answer of -2 for the sum of these two vectors on the horizontal component and 5 on the vertical component of that sum. Okay, A minus B, we're going to take A, vector A, and subtract vector B. Okay, and I can show the work right here. Okay, it'll be front component or horizontal component minus horizontal component, and then vertical component minus vertical component, to give you a final difference of -4 on your front component or horizontal component, -3 for your back component. Okay, and then if you're doing opposite of vector A, well, that just means take vector A, -3, 1, and multiply it by -1. And when you multiply by a scalar, you're just distributing it into both components. So that would be -1 times -3, 3, -1 times 1, -1. Okay, and that is the opposite of vector A. Moving to example 5, it says give the answers in component form and also in AI plus BJ form. So I'm going to show all of that as I do each of these answers. So in part A, we're going to go 7 times U. And first we want to establish that we understand what this means. This is your first exposure to IJ form. So this U right here can be written like this. I is like the X component and this is like the Y component. So I'll show you both ways to write it. Here's vector U in IJ form. You have 8I and you have no vertical component. This is the horizontal component when it's in IJ form, and this is the vertical component. So if you want to write it without the I and the J, then this is the symbol we use. 8 for the horizontal component, 0 for the vertical component. Nice, clean method for writing the horizontal and vertical component. So that's U. Now we're going to be giving our answer in both IJ form and also in just basic component form. This is what we refer to as the unit vector form also. Okay, and then we have this other vector, which is vector V, and you can see that they've given it in IJ form, and if you want to take it out of IJ form and put it in component form, then it's 7, 4. Okay, so now let's begin doing the answers. I'm going to do A right here. We're going 7 times vector U. So 7 times, I like to work in component form and then I'll give it in ij form as well. Okay, so there's vector u right there, and we're multiplying it by the scalar 7. So just distributing. This times this times this, so you have 56, 0. So there is the vector u multiplied by 7. If you want to give it an ij form, this is the I component, the vertical component. That's the one with the I, and then the back or vertical component. Horizontal component gets the I, vertical component gets the J. Okay, in part B. Part B, we're going 7 times u, which we already figured out. Might as well just go grab what we did in part A. When we do 7 times u, when we did 7 times u, it was 56, 0. And we are adding to that 3 times v. So 3 times v, and my v vector is 7, 4. So we have the 56, 0 for that u vector, 7 times u vector, and then this 3 times v vector is going to end up being 21 and 12. 3 times 7 is 21, and 3 times 4 is 12. So when we finally get to the part where we're able to add the vectors, it's front component added to front component. In other words, you're putting those horizontal components together, so that would give you 77. This plus this, and then 0 plus 12 is 12. And if you want to give that in ij form, it would be 77i plus 12j. Okay, 2 different forms for giving your answers. Part C, we're supposed to be doing v minus 3u, and we did already calculate 3u in part B, so we can just use that. Let's go ahead and take vector v. Vector v is just 7, 4. And subtract 3u. When we did 3u, it was 21, 12. That's what that was right there. This was me showing the work. So 21, 12. And then when you go ahead and subtract, it's just going to be 7 minus 21, front minus front, back minus back. Okay, that ends up, if you're taking 7 and subtracting 21, you get negative 14. And if we're doing 4 minus 12, we get negative 8. And if you want to put it in ij form, then it's negative 14i minus 8j. Okay, that's your I term. This is your j term. Okay, and that's part A, B, and C. That completes number 5. And then let me just check these real quick. 8074 were the original ones. And this one, I just wanted to make a comment that when you can give the answer like this, but if you do have a term that is 0, when you're giving it in the ij form, you can just list the one non-zero term that you ended up with. So you have that option, or you can list it like this. I believe they'll take it either way. So the other one was 77 and 12j. Then for part C, we had a 7, 4, and then we were subtracting 3 times u. And let me make sure that I think I grabbed 3v here, so I need to fix this. Okay, so this was v. V was 7, 4. And then right here, I have a mistake here. This I was supposed to do 3 times u, and I did 3 times v. So 3 times u would be the following. Let's correct that before I move on. 3 times u would be 3 times 8, 24. 3 times 0 would be 0. So then it would be 7 take away 24, and then 4 take away 0. Sorry about that. Glad that I caught it now. So then when you go 7 minus 24, you're going to get negative 17. And 4 take away 0, you're going to get 4. Needed to fix that right there. Okay, so once again, this was v right here, 7, 4, and then I was supposed to go 3 times u, and 3 times u was 24, 0, and I was taking one and subtracting the other. 7 minus 24 was negative 17. 4 take away 0 was 4. And so this final answer can be written as negative 17i. Plus 4j. Okay, this is the same thing as this. This is in ij form. This is in component form. Okay, moving on to example 6. Okay, so in example 6, this time what I wanted you to notice is that you're just being given 2 regular points in the xy plane. Notice that they do not have the symbols that vectors have. So these are not vectors yet, but you're going to turn them into vectors, and that's what this formula up at the top of the page is about. And we're going to use that for example 6. That's what I was referring to. So it says, suppose that you have a vector with initial point having coordinates x1 and y1, not necessarily at the origin. So these vectors could be anywhere in, in the coordinate plane, not necessarily with their initial point at the origin. And that's why this is position vectors with endpoint not at the origin. And the terminal point of the vector is called x2, y2. So you have 2 points, the initial point and the terminal point, as all vectors have. And so the formula for turning coordinates into vector components is the following. You're just going to subtract. You're going to go the x coordinate belonging to the terminal point. You notice the coordinates for the terminal point are x2, y2. So when you find your horizontal component, you're going to go the x coordinate from the terminal point minus the x coordinate from the initial point. Same thing with the y coordinates. Y coordinate from the terminal point, that goes first, then the initial point. So remember that formula. It goes terminal minus initial on the x's. Terminal minus initial on the y's. And so that's what you're doing here. So someone has to tell you what the initial and the terminal point is, or indicate it on a diagram. So it says here in this problem that the initial point is P. These are your initial coordinates, initial x, initial y. And then it says that Q is the terminal point. Okay, so we're going to turn this now into a vector, and we're going to give it in ij form, just like it says right here. So the vector v is just, okay, going into vector form now. So we're going to take the x coordinate from the terminal point. Remember, it goes terminal minus initial, whether you're working with the x's or the y's. So terminal x coordinate is 5. Initial x coordinate is -9, and you're subtracting. Okay, terminal minus initial x coordinate. Then for the y's, same thing. Get the y value from the terminal point first minus the y coordinate from the initial point. Okay, 5 plus 9, 14. -10 plus 6 is going to be -4. And so now you are in vector form as long as you're going terminal minus initial in using your coordinates and in moving to your vector. Okay, so the position vector is when you state it in the ij form. This is your vertical component. This is your horizontal component. This is your vertical component. Okay, I and j. This is what we call a position vector. And moving to example 7. Okay, here we talk about formulas for finding a vector. And the formulas that we're looking for, this is working off of an angle, so a vector as well as the magnitude of the vector, the angle of the vector and the magnitude of the vector in order to get the front and back component, in other words, the horizontal and vertical component. So it says a vector with its initial point at the origin this time is called a position vector. A position vector with endpoint AB is written as vector U, where A is called the horizontal component and B is called the vertical component. So what these formulas are telling you how to do is how to get A for the vector and how to get B for the vector. Okay, so this is, you want to get the horizontal component. It is just magnitude of the vector. That's what this is. It's how long the vector is, magnitude of the vector. That's what those little symbols mean. And sometimes in some books they'll put double bars. That just means the magnitude of the vector or how long the vector is. And they're actually just giving that to you. They're not making you calculate it, although you will have to do that in several subsequent problems, but they're not making you do it here. They're just simply giving it to you in the picture. It's 11. Okay, rest of the formula here goes that if you want A, it's magnitude of the vector times cosine of what's called the direction angle. Okay, that's if you want A. If you want B, magnitude again, but this time times the sine of the direction angle. Okay, so let's go ahead and do that. A is equal to magnitude of the vector is 11. And I'll make this look like ones, just so you don't think it's these bars right here. So it's 11 times cosine of 45 degrees. Cosine of 45 degrees, if you don't remember that, I'll just kind of remind you right here. When you're 45 degrees, the vertical leg, or in other words, the sine, is square root of 2 over 2. And this horizontal leg in your right triangle is also square root of 2 over 2. And the horizontal leg represents the cosine. So right here is square root of 2 over 2. And you can write this as one single fraction. This top times top, because 11 is the same thing as 11 over 1. So 11 times square root of 2 over 2. And when you go to do the back component of the vector, it's the same thing. 11, the sine is also square root of 2 over 2 because both legs are equal. when you're talking a 45 degree right triangle. So you're going to get the same thing for B as well. And then you write it in the form of a vector. This is vector notation. The A value, or in other words, the horizontal component, gets written in the front. And the vertical component gets written in the back. Okay, that's example 7. Moving on to number 8, where we are now going to calculate the magnitude ourself and also the angle. Okay, so in this particular problem, they're already giving you a vector. So you have the A value and you have the B value. When you're in component form like that, you are being given the A and the B value. So if they ask you for how long is the vector, which is what magnitude is, you're finding the length of the vector. Let's just say this is called vector U with components A and B, horizontal component A, vertical component B. So how long is the vector? That's given by this formula right here. It's just A squared plus B squared. It's really just like how we used to find the hypotenuse when we were doing Pythagorean theorem. And this would just be 3. Square root of 3 squared is just 3. Negative 1 squared is 1. So you're looking at square root of 4, or in other words, just 2. Length of this vector is 2. Okay, then looking for the direction angle, and they want you to have the positive direction angle. Okay, so don't give a negative angle here. And there's a formula here also. Tangent of theta is B over A. Okay, now you have to be careful here. You have to pay attention to what quadrant would this be in if we were thinking XY axis. What quadrant would that be in? Because that has a lot to do with whether we're going directly to the theta that we're looking for, or are we going to take a temporary stop at the reference angle, which will then lead us into the final theta that we're looking for, called the positive direction angle. Notice that, and I keep really harping on this, that the only time you're going directly to the theta is when the actual quadrant you're in is quadrant 1. You go directly to finding theta immediately. But the minute that the point you're talking about is in any of the other quadrants, 2, 3, or 4, you need to find the reference angle first by way of this tan formula. Then you can move to the actual real theta where this point is. Okay, so you are in quad 4 here. Okay, if you were to plot positive square root of 3, which is approximately 1.73, you would be over here and then down to negative 1. So you'd be in quad 4. Okay, so you're in quad 4, and you're going to have to take that into consideration when you do your direction angle. You're going to have to rotate from here to here, and that's going to be your theta. You cannot get that theta until you get the reference angle, which is right in here. Okay, so what we're finding with this tan formula is the reference angle. Now that's B over A. So B over A. Okay, B value is the back value, A value is this value. And if you want to get your calculator to help you out a bit, you can just go inverse tangent of this value, feed it in just like that, and that'll give you the reference angle. Now, if your calculator shoots back a value that is negative, it's because it's trying to obey, it's obeying the restrictions for inverse tangent. I don't know if you remember those from chapter 7, but for inverse tangent, you can be anywhere from here to here. So your calculator is going to give you something in there, and it's probably going to give you, it's going to give you a negative angle, because how can you have a tan value that's negative unless you're down here? It's not going to give you anything up here, but it will, at least what it's giving you can be used as the reference angle. So if you want to be able to recognize the angle that your calculator is so kindly trying to give you, you should put it in degrees. You could always convert it into radians to give the final answer in the form that the homework software pretty much demands most of the time. So the mode should be in degrees. Okay, so we started off with tan of the reference angle. We're using this definition right here. Just instead of saying tan of theta, we said tan of theta prime, the reference angle. Still using the same definition. This was B, this was A. Okay, then we turned this statement around into an inverse just by swapping these two. That's from chapter 7. This value comes up against the tan. Now it has the inverse symbol, and the reference angle jumps over and takes its place. So putting that in your calculator, check my mode. My mode is in degrees. Let me quit it out of there. Second inverse, okay, and it is -1 divided by the square root of 3. Close that up again, and I get -30 degrees. Reference angles can only be positive. So if this is 30 degrees, or in other words, pi over 6, let me just try and draw a bigger picture here so everything is not so crunched in. Okay, so we have this vector right here. This vector right here represents square root of 3, -1. And we wanted to find the direction angle. We found out through the tan formula that this reference angle is 30 degrees, which is the same thing as pi over 6, so that we can remember how to give our answer in not only degree form, but also in pi form. Now, I have yet to find the theta where this arm is right here. So in degrees, pretty easy. If you're rotating all the way around, almost made it back to 360, because your rotation starts at a place that's called 0. But by the time you come around full revolution, almost to 360, then you should be at a number close to 360. How much short of 360 did this rotating arm stop? 30 degrees before you got there. Therefore, this theta, yes, it can be called 330 degrees if that was the way that your homework software likes you to give the answer. Then yeah, sure, give it like that. Most of the time it wants it in radian form, so we have to practice with our fractions. Okay, let's think fractions. Another name for this, yes, it is called 2 pi. It's called 0, it's called 360, but if we're thinking radians, we need pi type names. This is called 2 pi, but I want to say 2 pi, the number 2, in terms of sixes. So I call 2 pi by this name, 12 sixes. That's the same thing as 2 pi. Well, if you're rotating and you're rotating all the way, stopping 1/6 before you get there. That's what pi over 6 is. It's 1/6 before you get to 12/6. If this little reference angle is 1/6 of a pi, then you're at 11/6. Again, let me move this over. I'm always writing too big, and then I'll have room to write the answer. This would be 11 pi over 6. Same thing as 330. Okay, I cannot emphasize enough the fact that every time you are in any quadrant other than quadrant 1, you must find the reference angle first and then find the actual theta associated with that reference angle. Final exam is filled with that particular concept. It was present in every single chapter, first introduced in chapter 6. Okay, we're going to do it again here. Practicing the difference between reference angle and the real final theta. Okay, so we finished by saying that in this problem, the final theta was, you could call it 330 for 11 pi over 6, and most likely you will be asked to give it in pi form. Okay, we're going to practice those same things. We had also found the magnitude. So this vector has a length of 2 and a direction angle of 11 pi over 6. Okay, the length is 2. The magnitude is 2. Okay, here we have another problem again. You are asked for the same two things. Find the this one only actually asks for the direction angle, so it doesn't ask for the magnitude. So it's just tan. Okay, again, let's signify that you are not in quadrant 1. If you're going to plot something that has a negative horizontal component, that's like having a negative x component and then a positive y component. You're just looking at the coefficients here. This is A and this is B. They have the same thing as x and y. So if you're going in the negative x direction, positive y, you're in this quadrant right here. You're in quad 2. Okay, that being said, since you're not in quad 1, you need to find the reference angle first. So instead of writing tan of theta, you're going to write tan of theta prime, finding the reference angle first, but using the same definition, B over A. Okay, so we know that we're over here somewhere. Just the y and the x-axis, just to orientate us. So tan of the reference angle is the b value 9 over the x value. I do not suggest putting this in your calculator without simplifying it. So 9 goes into 9 once, 9 goes in here once, so this is 1 over 1 square root of 3. It is negative. It's the same thing we just put in the calculator for the previous problem. Now, just in case you go blindly putting this into your calculator, but are forgetting some of the things that took place in Chapter 6, where we were first familiarizing ourselves with special right triangles, one of those being the 30, 60, 90 triangle, which had a short leg, a long leg, and a hypotenuse. Think about what's going on here. I mean, if you were going to represent what's going on here, and some students have made the comment that their calculator shot back 60 degrees or negative 60 degrees them. Why don't you put these values on your triangle and take yourself back to the very bare basics that you learned in Chapter 6, where we established how to tell what the short leg and the long leg is so that we could tell what kind of reference angle is here. Tan is always y over x. Therefore, this would be the y, this would be the x. Make a decision who gets the negative when you're representing it on a picture rather than a fraction. Because in a fraction, you can put the negative wherever you want, top, bottom, or out to the side. But in a picture, you better put it on the correct leg. This horizontal leg represents the x value. This vertical value represents the y values. Well, y values can't be negative here. So that negative goes here. That being said, look at the numbers that you have here. This value is less than this one. Put that in your calculator. You'll see that this is 1.73. So it's definitely the longer leg. But is it the kind of long leg, short leg situation that suggests 30, 60, 90? Most definitely. If you don't remember the formulas from chapter 6, it was said that the hypotenuse is always twice as big as the short leg. So you could use the Pythagorean theorem and you would figure out that that's 2. Not that we need the 2, because we don't need it. And also another relationship in a 30, 60, 90, not only is the hypotenuse twice as big as the short leg, but always the long leg is square root of 3 times the short leg. That is actually a formula for 30, 60, 90. That the hypotenuse is twice as big as the short leg. So if we needed this, yeah, it would be 2, but we don't. And the long leg, which is this guy right here, I know that this has to be the long leg because this number is bigger than that one. The long leg is always the short leg times square root of 3. And you can see that that's what this is. If you take this short leg and multiply it by square root of 3, just like this formula says, you get square root of 3. This has to be the long leg. This has to be the short leg. Always across from the short leg is 30 degrees, or in other words, pi over 6. Always. So if your calculator is shooting you back 60 degrees or negative 60 degrees, and you're thinking of mistakenly using 60 degrees for the reference angle, then you're forgetting all the skills that you learned for doing it by hand. That is very valuable because sometimes you need to be smarter than your calculator. It'll help you out a lot, but there's certain things that can't be fed into the calculator. So you have to know that 60 degrees isn't it, not based on the values that we have here. It's 30 degrees. Okay, so that being said, all this is the reference angle. It certainly is not the final answer. So if you're going to go with, hey, my reference angle, and again, to put this in the calculator, you put it in just like we did it right up here. I'm not going to write that all over again. You can turn this into an inverse statement by just swapping these two. And it would look just like this. Your calculator should be, and I would not feed it in like this. I would get rid of, I would, simplify. You're giving your calculator too much to do. Reference angle is 30 degrees, same thing as pi over 6. It can't possibly be 60. Okay, then if you want to find the actual theta, well then you have to understand how to use a reference angle. Actual theta is from the 0 mark all the way to where this hypotenuse is, which is really the vector. This vector right here represents -9 square roots of 3. See, now in this section, we used to call it the hypotenuse. Now we're just calling it the vector, and this vector represented by -9 square roots of 3, +9. You know, if you wanted to write it in component form, -9 square roots of 3, comma 9. That would represent this vector right here. And so to get from 0 degrees to there, well, let's see. We could do it in degrees if we wanted to. This is the 180 mark, also known as 6 sixths of a pi. 6 over 6 is 1 pi. We're going to give this answer both ways. So if we were rotating to here and we stopped 30 degrees before we got there, it would just be 150 degrees in degree style. if we were going to give it in pi form, then we'd say, hey, we were on our way to 1 pi, 6/6 of a pi, but we stopped 1/6 before we got there. So 6/6 minus 1/6, you're at 5/6. There is the answer in radian form and also in degree form. Your calculator will at least give you the reference angle and know how to correct yourself if you're seeing something that doesn't make sense in the calculator. Okay, moving on to example 10. Yep, there's 10 and 11. So in example 10, it says use the parallelogram rule to find the magnitude of the resultant. So if they're talking about resultant, they want this sum right here. All this is were some numbers to transfer to this picture. In other words, we took this and made a parallelogram out of it. Because in doing that, we create a triangle that we can work on using some of the laws that we learned in chapter 8. Law of sines, law of cosines. We'll talk about what works here. So all that happened is we constructed a side that, in this picture, that was opposite to the 8 and parallel to the 8, and also a side that was opposite to the 4 and parallel to it, and we got this parallelogram. This is the resultant that they're looking for. Okay, now you can leave the name that you see here, a plus b, just so you understand you're trying to find the sum of two vectors, the sum of this vector plus this vector, and you could just call it x to make the calculations a little bit easier rather than carrying a plus b throughout the whole manipulation. I want you to remember that in parallelograms, opposite sides are equal. So this was vector A, this 4 right here. So if this is 4, so is that. If you need it, it depends which triangle you decide to work with, the one that's right side up or the one that's flipped upside down. They're both equivalent. And if the bottom is 8, then this is 8. Okay, so this represents this. This represents this. Opposite sides are equal. So if this is 8, I'm allowed to put an 8 there as well. Another thing about parallelogram. In parallelogram, not only are opposite sides congruent, in other words, equal in length, and they also happen to be parallel, but also there are some things in a parallelogram that are true with respect to their interior angles. First of all, if you have forgotten two angles that intersect with the same side, such as the angles that I am pointing out, notice that this angle runs right into vector A. Notice that this angle runs right into vector A. So both of these angles are called adjacent angles. They both intersect with the same side. Adjacent angles in a parallelogram happen to be supplementary. Adjacent angles are supplementary. So, see the 60 degrees here? That represents this angle right here, 60 degrees. So if this is 60, and let me put this a little bit higher just so you can read it. That line's pretty thick. So if that's a 60-degree angle, and this is its supplementary partner here, then this is 120. Okay. Trying to fill in as many things as I can inside this triangle. So in this triangle that has, let's just say side A length 4, side B length 8, and a 120-degree angle between side A and side B, I want to find the side across from the 120-degree angle. I cannot use law of sines. I can't use Pythagorean theorem because these are not right triangles. So I resort to law of sines, law of cosines. The reason I can't use law of sines is because for law of sines you need at least one angle that you know the side across from it. You know the value of that side, and yet we don't. We have this angle, but we do not know the side across from it. 60, you don't know how much of this right here, how much of the 60 is that little angle right there. So what you're going to use here is some students are going to say, oh, but I knew that there was an 8 here, and the 8 is across from this angle. Well, this 60, part of it belongs to this angle, part of it belongs to that angle. You can't necessarily just split that up. So what you're going to do here is use law of cosines. If you have an angle, you don't have a pair where there's an angle and a side across from it that you know the length of, you go into law of cosines. So the way that goes is when you're doing law of cosines, you take the one angle that you do know inside the triangle, and you're going to end with cosine of that angle. And then that rule for law of cosines, it ends with cosine of the angle, and it begins with the side across from it in its squared form. So law of cosines okay, so the side across from the 120 degrees, x. Everything in it's a squared form for these first three terms. Then right after you get past the equal sign are the other two sides. So we use side called x, which really represents the resultant, a plus b. The other two sides are 4, or their magnitudes, 4 and 8, their lengths. And then the law of cosines goes like this, minus 2 times each of these lengths, but in their linear form, and ends with cosine of the angle across from this unknown side. Okay, as we try to clean this up, this will be 16 plus 64 minus 2 times 4 is 8, 8 times 8 is 64, minus 64 times cosine of 120. And you can feed it in as it is originally. I like to clean it up a little bit. So 16 plus 64, I'm going to feed this in 80, right there, minus 64 times cosine of 120. That'll be my x squared value. So feed that into your calculator. I got 112 for this value. And bring down that x squared. Okay, now you're at x squared is equal to 112. Remember, we called x, just gave it this name. It's really the resultant, the sum of vectors a and b. So if we take the square root of the left, we're going to take the square root of the right. The square root gets rid of the square. Square root of 12 is approximately 10.58. Why don't we just round to the hundredths place here? Okay, and the unit would be pounds. Everything was in pounds. This was 4 pounds, 8 pounds. You know, they're in pounds rather than meters or inches because they actually represent, you know, a force. A vector can be a force. Okay, and this is the answer. That is the magnitude of the resultant. It is how long the resultant is. The resultant is the sum of the two vectors. So this vector represents the sum. It has a length, and that is the length right there, also known as the magnitude. Just trying to get you used to the terminology that is used in this chapter on vectors. Okay, last problem in this section. This one says finding unit vectors that have the same direction. And we have the definition right here. A unit vector is defined as the actual vector is going to play the rule of the numerator so that it has the same direction and so that it has the same magnitude. We're going to be using the magnitude down at the bottom. That's what these double bars mean. You can use single bars around the vector or double bars, and that signifies magnitude of the vector. Okay, so this says find the unit vector having the same direction as this. So according to this formula, you're going to use the actual vector up at the top, which signifies that this is a -2i and a 5j. So it like signifies what quadrant it's in just by virtue of the signs that are apparent in the coefficients of I and j. So unit vector for this particular vector using the formula above is the actual vector divided by the length of this vector. That is what magnitude is. It's the length of the vector. That formula was introduced on the first, at the beginning of this section. Magnitude, you're just finding the length of this vector by squaring the coefficient of the horizontal component and squaring the coefficient of the vertical component. Okay, so this is -2i plus 5j divided by, this is 4, this is 25, so this is square root of 29. And if you want to split this up into separate components, you're also going to want to rationalize this. They typically do not want the radical on the bottom. So rationalized form, you would just be multiplying this by square root of 29 and this by square root of 29. But you're multiplying square root of 29 on the top by both of these components. So final answer in its most simplified rationalized form, -2 times square root of 29 on your I term. So I'll write it like this. I mean, you can put the square root of 29 right here, and then the I. I typically put the I at the end, over square root of 29 times square root of 29. Its denominator is just 29 now. And then also multiply it by the j term. So 5 square roots of 29 on that j term with a denominator once again of 29. And this is the unit vector. Having the same direction as the original. Okay, that is the end of section 9.4, Properties of Vectors.